today's lecture. I think I'm audible to all of you.
Yes, sir.
Yes, sir.
Okay.
Okay.
So my slide is visible.
Yes, sir.
So we were talking about the Kelvin's double bridge. Um, Before Kelvin's double bridge, we basically Kelvin's double bridge is modification of Wheatstone bridge, and as I told you that in measurement of small value resistances, um, the main challenge is lead and contact resistance. So this bridge method considered is considered as very good method for medium resistance measurement when the value of the resistance known resistance slightly high. But if it is smaller value, then um, this method is having issue due to lead and contact resistance. And any method which does not address the this issue will not fetch you the correct accurate measurement as far as low resistance measurement is concerned. Now we are trying to modify the Wheatstone bridge. What should we do so that lead and contact resistance can be taken care of? And here you can see that we tried it on the last turn. I explained it in detail. We means we are trying to we considered lead and contact resistance as a lump resistance. Here it is shown as a small r value, and if we are trying to balance it with the simple method of connecting your galvanometer at one side of the this considered lead and contact resistance small r, or other side. In both the cases your lead and contact resistance is coming into the expression of unknown resistance. And obviously we are not because this small value of this r resistance r, that is indicating, that is representing the lump resistance for the wire and contact. It is not possible to measure it because it is a distributed resistance. So basically when it is present in the balance equation and we are using this balance equation, if we know small r value and we are using under balance condition, we are using these expression to calculate the value of r, only then it will fetch you the correct result. Otherwise you will. So we actual balance equation in such situation is this, but we are calculating the value by this equation, so obviously the calculated value of final result will not be correct. So what is suggested? It is suggested that if somehow this is a conceptual solution that is suggested, if this lead and contact resistance is divided into two parts, instead of taking it in the one part, if it is divided, means by connecting the galvanometer in between, uh, if it is divided in two part R1 and R2 in such a way that ratio of R1 and R2 is equal to ratio arms, then it will be it means its effect will be compensated on the final result. This is what claimed, and then we discussed also, and we verified also, and then you can see that ultimately if this condition is satisfied, then you can see that your final outcome is this clean balance equation. Your lead and contact resistance is not introducing any error in your final result. So this is what we have discussed on the last turn. So this is what modification which is suggested, that if somehow we are able to divide the lead and contact resistance in arm S and R and S in two parts, R1 and R2, such that R1 upon R2 is equal to P upon Q. Then lead and contact resistance will not have any effect on your final result, that we had already verified. But this suggested solution is basically conceptual solution. Implementation of this is very difficult. So then we on last time we discussed that implementation, instead of because challenge is that where to connect the galvanometer so that this lead and contact resistance can be divided into two parts, R1 and R2, such that R1 upon R2 is equal to P upon Q. So the physical modification that represents this um, uh, conceptual modification is this: instead of connecting in between, two real resistances are used, P and Q, because you can see that this is the point M, this is a point N, and this is the lead and contact resistance. uh, so so from M and N, real resistances P and Q are taken, and such means the value of these two resistances are taken in such a way that ratio of these two resistances is equal to the ratio of the original ratio arms resistances. So this is what claimed that if we are making the connection of modifying the connection of the Wheatstone bridge like this, then it will represent whatever that has been suggested conceptually. So this is what is called inception of Kelvin's double bridge. So this is the resultant circuit which is shown here. It is called Kelvin double bridge. Why it is called Kelvin's double bridge? Because this bridge is having two set of ratio arms, and that's why it is called Kelvin's double bridge. So you can see that this point D is this point D. Now this is claimed that this bridge, when it is balanced, then it will satisfy whatever solution that has been suggested in this modified Wheatstone bridge. It will be achieved. If anybody is having any question regarding whatever we discussed till this point, we discussed in the last time. So if anybody is having any question regarding whatever we have discussed in basically the inception of Wheatstone bridge, Kelvin's double bridge, you can ask please. जी, किसी को कोई प्रॉब्लम है, कोई इशू है तो आप पूछ सकते हैं. ठीक है. Now we'll move forward. It is written here: the second set of ratio arms P and Q is used to connect the galvanometer to a point D at appropriate potential between points M and M, and to eliminate the effect of the connecting lead of resistance R. So this is what is the solution that has been suggested to physically modify your Wheatstone bridge to achieve the conceptually suggested compensation lead and contact resistance compensation method. Now we'll try to you can say derive the balance equation for this bridge. So there are many ways that has been in different books. Many ways are given. The most easiest method I found in one of the books. So you can see that if you look upon this part of the bridge diagram, then it is making a delta P, Q, and R. This is R, this is P, and this is Q. And now we connect, we transform this delta into star. So resultant diagram will be like this. Means we transform this delta into star, and this is the resultant diagram, and this is formula you must have studied in your first year or second year. that E will be equal to PR upon P plus Q plus R. Anyway, that is what is delta to star conversion formula. So if you look upon this diagram, what does we achieve after transformation? What does we achieve? जी क्या 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 फाइंड आउट हुआ? The circuit diagram is simplified. जी बताइए.
Yes.
Now it is if you look upon this diagram, this circuit diagram, it is simple 4-arm bridge, whereas one of the arms of the star that is representing basically this delta is in series with the galvanometer. So this particular resistance will not play any role when your bridge is balanced. When your bridge is balanced, so this will not play any role. Anyway, now we'll balance the bridge, and when the bridge is balanced, then obviously P upon Q will be equal to R plus E divided by G plus S. So this is what we have written, and then we modified it, and finally, because you know that as far as F, G and E are concerned, they are not original bridge parameters, you know, because we transform it just to simplify the circuit so that we can find out the balance equation and all. So then we put value of G and E from this transformation formula, and we put here. So this is the balance equation for the Kelvin's double bridge. But we were claiming that it will compensate the lead and contact resistance like Q and R. Sorry, R is still present in this expression. This means with this bridge also, if you require to find out the correct value of the unknown resistance, which is very small in value, then you are required to find out the lead and contact resistance, and this is a challenging task every time. So what is your comment? What is your comment? जी बताइए. First of all, if you are having any difficulty in understanding any of the steps in derivation of the balance equation, then let me know, and then I want your comments on the final outcome. हाँ भाई बताइए, कुछ फरमाइए, कुछ बताएंगे, कुछ फरमाएंगे आप लोग, तब तो गाड़ी आगे चलेगी. नो कमेंट्स. भाई सो गए क्या, अभी जग रहे हैं? सुन रहे हैं भाई? मैं सुनाई पड़ रही मेरी आवाज?
आवाज आ रही है.
यस सर.
तो ये चीज समझ में आ गई आपको जो मैं समझाने की कोशिश कर रहा हूं? जी नहीं समझ में आई तो बताइए, फिर मैं और फिर समझाऊंगा आपको. जी
आ गई
सर, आ गई.
अच्छा, तो मैंने जो क्वेश्चन पूछा, अगर सब बात समझ में आ गई आपके, तो मैंने जो क्वेश्चन पूछा कि ये सारी चीजें तो हमने इसलिए की थी कि we should able to find this kind of equation, and it was claimed that this particular circuit is basically a representation of this concept, physical representation of this concept, and this concept provides the solution for the lead and contact resistance compensation. But you see in final outcome, final expression that we have derived, your equation is not as simple as P upon Q is equal to R upon S, but it is still having the lead and contact resistance value in it. So in this case means if we know lead and contact resistance, then we can use the initial equation also. This equation. Here you see this equation. If R is known, we can calculate the value of R, unknown resistance, from this equation also. A correct value will get. But generally, it is very difficult to find out R every time, small r of the lead and representing lead and contact resistance. So what is your comment on it? That's what I am asking. How this expression will achieve that was means the compensated equation. We want R is equal to P upon Q into S.
Sir, capital P upon capital Q is equal to small p upon small
That's
q.
what
And method
I was trying to extract from you. I don't know. It's very obvious that we are claiming that P upon Q is equal to small p upon Q. That is the expression here. You see, this is the precondition. So once this will be equal, obviously this part will go, and then so it will provide the compensation for the lead and contact resistance, and your final expression will be this. So this is how Kelvin double bridge is basically the modified part of modification of the Wheatstone bridge, which takes care of lead and contact resistance. And this is how then we discussed the inception, and then the physical from conceptual circuit diagram to the physical realization of that concept, which leads to the inception of Kelvin's double bridge. And then we analyze it, and finally we are able to find the expression, final expression for balance equation for the Kelvin's double bridge. And here we can see that if these two ratios of two set of ratio arms are equal, then obviously your lead and contact resistance term will not be in picture, and you have a clean P upon Q is equal to R upon S kind of equation. And this way Kelvin's double bridge takes care of lead and contact resistance, so it is most suitable method for measurement of small resistance. This is fine to all of you?
Yes.
Now another method is potentiometric method. So how will you what do you know about the potentiometer? You people had performed the experiment also. So I want to listen something about the potentiometer from you. Yes, please. By the time you think about it, so I'll take the attendance of some of the students. Respond your roll call, please. Roll number 1. Roll number 2. Roll number 3. Roll number 2 present है भाई. Anyway, आप chat box में message डाल. You are not properly audible.
Yes, sir. डाल रहा हूँ सर. ये ओके सर.
क्या है आप सवाल पहला बताइए, क्या है आपका रोल नंबर, क्या है आपका?
हाँ भैया.
2 sir. 2.
रोल नंबर 3.
Present, sir.
4.
Present, sir. Roll number 4.
5.
Present, sir. Roll number 5.
Okay. 6.
Present, sir. Roll number 6.
7. 8.
Present, sir. Roll number 8.
9. 10.
Present, sir.
11. 12. 13. 14.
Yes, sir. 14.
15. 16. Back to the potentiometric method. So I want to know what is the potentiometric method. Although here we are using it to measure small value resistance. So ultimately I'll ask why this method. First of all, I'm asking what is this method? What is the application of this method? and the why do we use it for measurement of small resistance? These questions I want that, because you are already aware of potentiometric method, and you must have performed the experiment also in class 12th, as well as in your first year engineering, also in physics lab. You must have performed the experiment. जी, कोई बता सकता है?
The potentiometer is a three-terminal resistor with a sliding rotating contact that form an adjustable voltage divider. And so the potentiometers are commonly used to control the electric devices such as volume controls on audio equipment. So it is also used in joysticks also. So it is rarely used to directly control the significant power. Since the power dissipated in the potentiometer would be comparable to the power in the controlled load, sir.
अच्छा भाई, ऐसा तो कुछ नहीं है भाई, हैं? Power dissipation is a problem in potentiometer. So we have to have this resistance here. We are putting this resistance just to control this current, you know, so that there is not excessive power dissipation, so that your wire should get heated up. What means, can you recall what you have done in your laboratory using potentiometer? You must have done an experiment with the sliding wire and having joystick, and then
Yes, sir. Yes, sir.
then null deflection. तो क्या किस लिए किया गया था, वो क्या किया था?
So basically, in a potentiometer, the entire input voltage is applied across the whole length of resistor.
क्यों करते हैं?
So,
Why it is done?
so,
What is the objective?
sir, to adjust the output voltage.
To
Adjust the output voltage, sir.
देखिए आप, anyway, anybody else who want to speak on this, respond on this query? Anybody else? Listen carefully. As the name suggests, potentiometer is used to measure the potential difference, electrical potential. That's why it is called potentiometer. Although as far as the topic at this here is concerned, we are using this potentiometer for measurement of small resistance. So potentiometer is not mean to measure the resistance. Obviously it will be it is used for measurement of electric potential. That's why it is called potentiometer. And it is it is considered as a standard method for measurement of EMF or electric potential. Means it is standard method, means it is very accurate method. Like I'm giving you why means we can measure the we can use the voltmeter to measure the voltage of any source, but this is not considered as very accurate or standard method because it is having problem. So that's why I made this diagram here. If this is a source, voltage source, and we are trying, or a part of the circuit whose potential we are interested in finding out, so we connect a voltmeter across it. So if this is a source and this is your internal resistance of the source, so obviously when you will connect the voltmeter, so voltmeter will draw certain amount of current from the source. So whenever it will, means if you measure the voltage across the source, when your voltmeter was not connected, then it will show you the correct voltage. Means what I'm saying, so when this is the situation, so, and this is your voltage source. Suppose it is V. So when it is open, then obviously here open circuit voltage will be this, whatever is the voltage of the voltage source, because this is the internal resistance of your voltage source. Because we are not drawing any current, so there is no drop across it. Now if we are connecting a voltmeter here, so what will happen? Because current will flow, although this current will be very small, because voltmeter internal resistance or impedance is very high. So this current will be drawn, and because of that, the voltage drop will take place here. So obviously, whatever voltage that will appear here, it won't be the voltage of the source, but voltage of the source, it will be basically Vm, voltage of the source minus voltage drop across the internal resistance. So Vm will be equal to V, that is what we want to measure, minus IV RV. So your measured voltage will be less than your measured voltage will be less than your voltage value that we want to measure. So this is called basically loading effect. Your meter is loading your source or your circuit. So this is basically whatever voltage will be indicated, it will be erroneous by this. So this problem can be taken care of if your voltage measurement circuit is not drawing, it's not loading the source. So this is what happens here in potentiometric method, because it is a null method. So whatever voltage means at null, the source, you are not drawing any current from the source. Now I'm trying to explain that you are already aware of. I know you have already studied, but just for the sake of repetition, because we are going to use this method to measure the small resistance, so this knowledge is required. That's why so what is done, first of all, what we do, this is a typical potentiometer, sliding wire potentiometer. So we drop a voltage from a standard voltage source, whose voltage is accurately known, across, we drop this voltage across the sliding wire. And this is the resistance that I had shown, variable resistance, to make sure that excessive amount of current should not flow through the wire, because that will heat up the wire, and because of the heating, the wire resistance will change. So to avoid that kind of situation, this current regulating resistance is used. Otherwise, it is not having any function. So here, this voltage is dropped across this wire, and we know the wire resistance per unit length. Now this is the source whose potential we are trying to measure. It is unknown. Potential of this voltage source is not known. So what we do, we measure this voltage source, means we connect it like this, and then we compare the potential of this voltage source, whose voltage is not known, with the potential drop across the wire. And when these two potentials will become equal, then your galvanometer will show you the null deflection. Means if even this voltage is more than this voltage, then your current will flow in particular direction, because your current always flows from higher potential to lower potential. And when this voltage is more than this voltage drop across the wire, section of wire, then obviously your current in other direction it will flow. So we'll by sliding here, we'll try to find out the voltage exact. We try to match this voltage, and wherever the voltage is matched, means exactly, then galvanometer deflection will be 0, and we note down basically the length of wire from starting, and this length we try to find out. So generally, what is done, we require a voltage, unknown voltage source, who's just to find out the voltage of unknown voltage source, and then we require a known standard voltage source also. So we perform the experiment with the unknown one, and means like V, and then we get the length L1 at which we get the null deflection, and then V2 and L2 at which we get the null deflection for the known voltage. Suppose this is your known voltage, standard voltage. So I had written here E1 and E2, EMF of the battery E1, EMF of the battery B2. E1 is to, one thing is very important, that whatever batteries you are taking here, voltage sources E1 and E2, their voltage should be less than this voltage, because only then you will find the balance, means length within the, otherwise because your drop will be less than the voltage, this voltage, then it will be very difficult. Means you won't find the null deflection within. So this is very important condition, that E1 and E2 must be less than the EMF of the supply battery. So as you know that at E1, suppose equation is L1, means you are finding the null deflection at length L1, and R is basically the resistance of the potentiometric wire per unit length. So when we will multiply R with L1, so you will get the resistance of that section. If suppose it is L, so R, we know, so R into L, so we'll find this is the resistance of this section, because R is the resistance of the potentiometric wire per unit length. So when we will multiply this small r with the length of the wire, we'll get the total resistance of that section of wire. So that's what I've done. And when we'll multiply this I, because you see, this is the current I which will flow when it is potentiometer is connected to the battery B. Now when there is a null deflection, this means no current is entering into the potentiometric circuit, and no current is leaving from the potentiometer circuit to this circuit. So whatever current that was originally flowing when we are not connecting jockey to the same amount of current will flow when there is a null deflection. So this current, obviously, when we'll multiply this current with the resistance, so it will give you the voltage drop across that section, voltage drop across that section of wire. Now, when we are putting E2, another source, and then obviously your null deflection is found at length L2. So this is the drop across that L2 section of the wire. Now we'll take the ratio of E1 upon E2. So finally we'll have L1 upon L2 because IR remains same. So L1 upon L2. So we can find the unknown resistance in terms of known resistance here. This is the known resistance. And we can have E2 upon L2, we can write voltage gradient, the voltage drop per unit length. So we are basically required to find out the length of the wire which balances the source resistance. And once you are able to find it, so this is how your potentiometer, and why it is considered as an accurate method. You know, we are comparing the unknown resistance voltage source with your voltage drop across the sliding wire of the potentiometer. When both the voltage potentials become equal, then it is this method, this section is not drawing any current from the means this potentiometer is not drawing any current from the source whose voltage we are trying to find out. Like this here, in this case, this is the source, its voltage we are trying to find out using certain meter, and this meter itself drawing some current. So here you can see this is your potentiometer, and when it is null, then it is not drawing any current from the source. So it is not loading the source at all. So whatever error that was taking place because of the loading effect here, it is not present because it is a null method. So this is considered as the standard method for measurement, and that's why in the laboratory you must have done this experiment with the title, with the objective to calibrate the voltmeter using potentiometer. And you must have calibrated. So what we do, we measure the certain voltage with the help of voltmeter, and then that voltage is measured with the help of potentiometer. If both the voltages, whatever we have measured using potentiometer, using this formula, and whatever reading we are getting in the voltmeter, if they are same, then we'll say that the voltmeter is fine, it is giving accurate result, measurement result. But if there is a difference, then we'll say that voltmeter is not accurate. So is it fine?
Yes, sir.
If you are having any question regarding potentiometer, because we are yet to touch the method for which means here we are talking about the potentiometer. So potentiometer is used to measure the electric potential, and it is considered as a standard method because it is a null method. So it does not load the source whose potential voltage we measure with using potentiometer. So it is considered as a standard and very accurate method. So if you are having any query regarding the potentiometer, how potentiometer is used to measure the electric potential. Now, how the potentiometer small resistance, because you know that in when we talked about the small resistance measurement using voltmeter meter method. So here you can see that voltmeter we are using here. Obviously, voltmeter will draw small amount of amount of current, and then there is a lead also, so that we will lead to the error. So here, because we are connecting here, instead of voltmeter we are connecting a potentiometer here. A potentiometer we are connecting here. So obviously, when the potential drop across the resistance, unknown resistance, is equal to the potentiometric drop across the potentiometric wire, then there will be no current. This current will be zero because it is a null method. It won't draw any current. So whatever error that is taking place because of this loading effect, in case of voltmeter, will not take place here. And by measuring the potential across unknown resistance accurately, we can find out the resistance. So here you can see that this is your potentiometer, whatever we have discussed, and we are using this potentiometer to measure the voltage drop across the unknown resistance and across the known standard resistance, and they are connected in series. This is your circuit. So here what we are doing, we are connecting a unknown small resistance and a known standard small resistance. Means this resistance is in the range of this resistance. So both of them are small resistance, and they are connected in series, and this series combination is connected across a voltage source. So obviously, because of this voltage source, a current will flow, and that current, the voltage drop will take place across R and as well as across S, and value of S is accurately known, R is unknown. Then what we do, we use potential method to measure the voltage drop across the R as well as S. So you know, when the potentiometric method is used to measure the voltage drop across the RS, then it won't draw, your potentiometer won't draw any current. So the wire while there will be no drop across the lead and contact resistance, and this will not come into the picture, and you can measure this very accurately. So here you can see that ER is the voltage drop across the unknown resistance, and ES is the voltage drop across the known standard resistance. So obviously, because when you will find the null deflection using potentiometer, so this circuit current will not be disturbed, because no current will be drawn from this circuit, or or fed into the circuit. So this during null deflection, your current will remain same. So that's why voltage drop across the unknown resistance will be IR, and across the standard resistance will be I into S. So ER upon ES, you see ER upon ES is equal to R upon S. So you know ER upon ES is equal to LR upon L1 upon L2, means LR into LS. So here you can see by measuring the length of the wire at which you are getting null deflection. In case of R, it will be LR. In case of standard resistance S, it will be LS. So the R will be measured in terms of LR upon LS into S, where S is known standard resistance. So this way, the potentiometer method indirectly can be used for the accurate measurement of small resistance. And this way, because it is a null deflection, so it takes care of null deflection method. So it takes care of lead and contact resistance, because your lead and contact resistance will not come at all in picture, because no current is flowing through the wire when you are getting null deflection. So it won't affect your final measurement. Although it is not direct method, potentiometric method is not mean to measure resistance. It is mean to measure potential, electric potential. So by measuring electric potential, we can very accurately measure the resistance. This is the method. So if anybody is having any question, you can ask, please. Is it fine? Is it fine to all of you? Should we proceed?
Yes, sir.
Okay. Now, this is all we means these three methods, all three methods we have discussed. As far as small resistance measurement is concerned, ammeter voltmeter method, Kelvin's double bridge method, and potentiometer method. So these methods are prominently used for measurement of small resistance. When your resistance value is very small, or there is a small change in resistance also, then in that case we use any of these methods. And Kelvin double bridge is considered as an original method, a good method for measurement of small resistance. So all these methods we have discussed. Now I'm going to discuss the measurement of large resistance. So first of all, we'll discuss obviously the challenges in measurement of high resistance value, and then we'll discuss different methods which are used for measurement of large resistance. So as I told you earlier also, there is always means not only resistance measurement, any parameter which if you want to measure, then measurement of large values and measurement of small extreme values are always challenging. So as far as measurement of resistance is concerned, if we are talking about the high resistance, means your insulation, mostly insulation resistance. So there are different challenges. I tried to list these challenges here. So first of all, if the last point, I'll take the first. If you want to measure, because first thing which is told here, that if we are interested in measuring the large resistance values, so obviously we'll put it in the circuit, and then we have to supply the voltage across it. And because this resistance, large resistance value, if we are having a large value resistance or insulation resistance we are trying to measure, in both the cases the resultant current will be very high, very small, and because your resistance is very high. So even to get the significant amount of small significant amount of current, we require very high voltage source. So that is also one of the issue. Fairly high voltages are used in test in order to raise the current to a reasonable value in order to be measured. So these are the challenges. Now, another challenge is that suppose you are having an insulation around a resistance, a large resistance. So I had made it, means suppose this is your resistance, which whose value is very high, and we want, and around it there is insulation. So your insulation, because resistance is high and your insulation is also high resistance, so the insulation resistance as well as the unknown this resistance of the resistance element will be of the same, means comparable values. So that will lead to the problem of leakage current, because a current will flow through the body of the resistance and through the surface of the insulation also. So this whatever current which flows, because we are not interested in finding out in measuring the leakage current, we are interested only in the value of the current which is passing through the resistance. So means we are interested in the conduction current. So this leakage current is basically means this will lead to the and this is happening because your actual conduction current will also be a small value, because your resistance value is small, and your leakage current will be also in the same. So this leakage current, so if we are measuring by voltmeter ammeter method, you can see by taking here, we are putting a ammeter here, so we are taking the voltage upon current. So this current is basically, this is what we want, means actual conduction current if you are taking the voltage across the resistance and actual conduction current. So this ratio will fetch us the true value of the resistance. But actually whatever reading you are taking by connecting a series ammeter here, so what will happen, your ammeter reading will be equal to the conduction current as well as leakage current. And this leakage current is a big issue here, because the value of the leakage current is same, means it's around the same value as the conduction current, because your resistance is very high. And this leakage current is coming into the picture because very high value of voltage is applied to get the significant amount of current. So this is what one of the problem in measurement of high resistance is the leakage current. Leakage current introduces large error in the resistance. So this is the measured value and this is the true value. So this is one of the challenge. One of the challenge is potential challenge, you can say, is the leakage current. Leakage current basically introduces huge error in case of measurement of. How do we take care of it? That we'll see. This is the main challenge. There are the other challenges also. Then there is the, because we are talking about the very high insulation resistance, very high resistance values. So, and generally insulation resistance. So you see, if this is an insulation whose resistance we are trying to find out, then we have to put the electric contact at one side and electrical contact at the other side, and these contacts are made up of conducting material. So this particular structure will be of capacitance. We are having very high resistance insulation in between the two contact conductors. So this will become a capacitor, and this capacitor, if there is a formation of capacitance, then there will be a lot of static electrostatic charges, stray charges will, and this stray charges will affect the measurement of resistance, and that is another issue. So stray charges on the capacitance, because here we are not connecting any capacitance. The experimental setup itself is becoming a capacitance, and then there are the stray charges that will introduce the error. And then there is a problem of dielectric absorption current. First of all, when you are, because this is becoming a capacitance, so when you will connect to the voltage source, so initially a huge amount of charging current will flow, but although charging current will die down, means after some time, depending upon the time constant of the circuit, it will decay down to very small value after some time. But if we are taking that current, initially the means we are noting down that current which is also having a, so we are only interested in conduction current. So if initial charging current is there and we are not waiting and we are noting down this current, then again whatever resistance value you will calculate with that current which is also having a charging current component, so that will also lead to huge error. Then there is a dielectric absorption current. So I'm not going to explain what is dielectric absorption current, so but I'm telling you the name. So challenges in measurement of small resistance are basically the leakage current that is considered as a very potential source of error in measurement of high resistance. So obviously whatever method we are using, we should have a way to tackle the leakage current. Then stray charges is another issue, and then your initial charging current, and finally the dielectric absorption current. So as far as the charging and dielectric absorption current is concerned, these two currents, they decay down after some time. So whenever we are using to measure, we are measuring the large resistance, then after connecting the source to the resistance, we are required to wait so that your charging initial charging current and dielectric absorption current should decay down to minimum value, or it should be completely over. So this way your charging current and dielectric absorption current can be taken care of. But as far as leakage current is concerned, it will continue to flow, and we require a special method, special ways to take care of it. So we'll discuss the dielectric absorption current, and then how do we take care of the leakage current, and then what are the methods which are used to measure the high resistance, which takes care of all these issues that we are discussing. They are considered as the challenges in measurement of high resistance. So we'll discuss it on the next turn. If you are having any question, whatever I described for the as far as the measurement challenges of the high resistance are concerned, you can ask on the next turn. Okay. So I'm closing my today's discussion here only. Now respond your roll call as far as